But like,
That's awesome.
So it turns out that it's possible to form a completely iterative version if you can completely get rid of this recursion that you're going to do here. This will blow up your stack if you like in any programming language. There's even benchmarks online if you do a trivial operation recursively forever, how many operations you get in until the programming for the language or the what do you call it? Whatever runtime engine you have explodes. Does anybody know, like this is just kind of like real life, does anybody know in what situations you can include tail recursion and it's not a problem? Have you heard of this before? This is real life. This happens. So, sorry?
When you're returning the same value?
First of all, do you guys know what tail recursion is?
Yeah.
Okay. Well, I got some mixture. So tail recursion is when you make a recursive call to a subfunction at the end of your function, or the end of your operation. And so it turns out that some compilers are optimized to deal with tail recursion, which is really nice. And all they do, because tail recursion is a trivial form of an algorithm to turn into a iterative algorithm, is they'll do it for you. It'll save you from yourself. But so software development languages like the .NET libraries and stuff like that, you can actually get away with including tail recursion. It's really cool, and so you can make these really simple algorithms knowing that the compiler is going to optimize them, maybe. And so you should check and make sure that they did, or else your algorithm might explode on non-trivial cases. But a lot of languages, like PHP, JavaScript, they're not optimized, so you're just going to blow things up. It's a good idea to be in the habit of at least writing something like that, if not writing a fully iterative version like what I'm going to write here. So yeah. So all we do here is, for the fully iterative version, we just initialize these guys. So to be careful to build from the bottom up here, or else it obviously won't work. So we do this first. This is our initialization. And then this is the simplest algorithm in the world at this point. Let's talk about this for a second. Because on your assignments, you're going to have to reason about stuff like this. So I kind of want to discuss it a little bit. When you think about these two versions, why would you choose one over the other? Under what circumstances? And there's a really, really, really good reason why given different operating conditions, you might want to choose one over the other. So you can get to that by think about what kind of ends are you going to get. Does anybody want to sort of shoot me a guess? So if you have n equals 100 or n equals 10, what are the algorithms going to do? So you have n equals 10, how many recursive calls are you going to make? R1. Okay. How many elements are you going to have to calculate for n equals 10? So imagine that you have a complete set. You have 1,000 elements, and somebody calls it for the 10th element. Which algorithm is cheaper in that case? So with the iterative version, the idea is at the beginning, you run through all your elements and do all the calculation at the outset. So given this large, you might have 10,000 items. You might have 20,000 items, and you're going to run through all of them initially and calculate them all. So, you know, depending on your application, that might be a really bad idea to do every time you call your algorithm. If you're going to save this array for a while, this solution is actually not that bad, especially if you know that you're going to be starting with small values of n. If you're going to call n equals 5, then you're going to call n equals 25, then n equals 100. This is actually way more efficient in that case, in terms of responsiveness. And these are the kinds of trade-offs you should get to the point where it's just obvious. You know, you're like, oh, well, we're building a giant array at the beginning here, and that array is not built. You know, you initialize once, but that's different than maybe considering the maximum. Or maybe when you initialize your array, maybe the null values are fine. You don't even worry about it. You just block off the memory. Or maybe you have a sparse representation. You don't have to worry about it at all. So you could just grab the memory and not even think about it. And that's the general idea. So it might be, this initialization you do up here might be trivial, whereas this might be a lot more work, depending. Yeah. So I kind of want to outline the general dynamic programming paradigm now in practice. And to be honest, I kind of want to ask you guys what you guys are thinking about it. So what's the first, if you want to consider a dynamic programming approach, what's the first thing you have to notice about your problem? Yeah, that's definitely one of the things you have to notice. I know that is like number 2. Or, well, you're right. But really, the overlap part, so the idea that the substructure of the problem is optimal is separate from the idea that they might overlap. I mean, if you just have a system or a problem that can be divided into optimal subproblems, but you don't have this, maybe it just turns out that you just have a linked list of tasks to do, you know? You don't really get much benefit from considering a full dynamic programming solution. It's really, you're just dividing stuff up and attacking small pieces. It's not the same problem. Does that sort of make sense? It's only when you have this sort of recursion that happens. Where the problems really overlap. Does overlapping have 2 P's or 1 P? Just we're all computer scientists. Can't stop. I can't even do it with my consensus.
Suppose so.
2 P's? Okay, great. I feel less bad now that all the UT computer scientists get into it, so it's awesome. We should be embarrassed, guys. Okay, so after these 2 things are considered, what do we want to notice? So we know that, we're attacking a problem. We know that great. The optimal solution can be characterized by dividing up sub-solutions, and those solutions kind of overlap. What's the next thing we want to consider doing in that situation? So there might be a way to express, it's kind of a bottom-down approach. Greedy algorithms are really bottom-up. And we've seen the difficulty that you encounter when you try to think about growing to this faraway optimal solution from that far away. And that's why they're difficult to think about. But luckily, we can do the opposite here. So really what we want to do is think about the idea that given this top level, high level problem, that we just need to specify it in terms of the next optimal solution down, like the next level down. So we can split it up at once, you know. If we can consider it as cases A and B, make those two optimal solutions make this solution optimal. And it's great because you can abstract away the difficulty of dealing with those problems. Right? Because then when you get to those problems, they are in turn a problem that can be abstracted away to the next lower level. And then at the end, it's trivial. You know, you have something that's really like maximum or not. And so it takes care of that for you. So it's the idea of having recursive structure. So if you can find recursive structure, then you've pretty much got the problem sorted from a dynamic programming perspective. But you can't write that algorithm because it's really bad, because it's probably, especially if there are indeed overlapping subproblems, going to take exponentially long to calculate. So that's when you have to use memorization or an iterative algorithm. So this is all fine and good. We've already talked a lot about something that actually kind of does a better job than this in the course, in terms of solutions. Does anyone kind of want to tell me what that approach is? I kind of hinted already. So what's in general even more efficient than doing this dynamic programming, or at least as efficient? And I'm just mentioning this because if you can do it, then it's the best approach. And it's a property of a problem that you can show, and it has to do with making the best choice locally, which can be really easy to consider. Yeah, greedy. So sometimes you might have a greedy choice property. Meaning that the locally optimal choice leads to a global optimum. And these are non-trivial usually. If they're hard, you know, to think about. These are easy. Like, I mean, the easiest thing here is this. You know, people do that all the time. There's nothing impressive about writing a really cool 3-line recursive algorithm. Everyone can do that. It's not that interesting. What's really interesting is if you can take that, we're going to work through an example in a minute where we're going to take the recursive structure and we're going to show, or we're going to show a less trivial example than compared with the activity selection. It's still simple once you start formulating it, but before that it's not. And this is kind of like, I really want to give this to you guys as your general attack plan, especially on the finals and assignments and midterms and things. You should just rhyme through this. Okay, so what's the structure? And this will, you know, going through this, you might end up here, but you'll be better off even if you end up here than if you just try to think, oh, what's the greedy solution first? You might end up making a mistake. But if you can really identify what's the substructure of the problem, how do they overlap, how does the recursion work, can I form a recursive solution, and then after that you start to think, well, wait a minute, what if I just choose this? And then you'll almost have worked through all the things that you need for your proof as well by doing that, because you'll have considered a lot of problems along the way. So, you know, keep that in mind. So there's a less trivial, very fun algorithm we're going to talk about. When I say fun, I'm being facetious. It's really boring. Who likes matrices? Does everyone love linear algebra and matrices? Because we're going to talk about them a lot. it turns out that this is a really cool sort of optimization problem to talk about because the recursive step is not trivial. And because it's similar to other problems we're going to tackle in the future. Okay. So let's consider matrix chain multiplication. So when I get excited about matrices, you guys got to help me out because no one is particularly excited about matrices. You know? I'm trying my best, but I hope to convince you it's kind of interesting. So we're going to be given a set of matrices. Let's call the entire set of matrices R, and they can be considered as such with the following dimensions, and it helps to have it as a picture somewhere for the rest of this example. So right away, like the columns are the index plus 1. All right, so this is the kind of the problem setup. Initially, and the goal is to find the best bracket placement. So given we want to do this multiplication, so goal with cost or minimum computation. The general assumption we're going to make is that the number of multiplications is an indicator. Really long words. So that's the sort of initial problem set up. Let's see, I'm going to go to this board over here. Okay. So yeah, for some set, and this might take some convincing. For a set, you can denote the amount of multiplication. So we're going to say there's no brackets. I hope to convince you that the number of multiplications, let's say number of mul, is d0 times d1 times d2 plus d0, d2, d3 plus d0, dn, dn plus 1. Does anyone think I'm crazy by doing that? It's not intuitive. When I started going through the notes here, I had to convince myself. I would suggest working through a trivial example with just like a few elements and to try to do the multiplication. And it turns out that this is true. It's weird though. It's weird, but it's true. And if we take some sort of arbitrary set of four things, so if we consider a bracket for the bracket, the bracketed set, it turns out that the number of multiplications is, so we're going to do this one first. And then we're going to start with the D zeros. So you see what we did there? Basically, the only real difference is this. It's kind of weird. Did anybody see any sort of ideas about how we might be able to optimize this process? It's not trivial.
Just.
Yeah, sure.
What's D again? Like what?
Oh, sorry. D are these dimensions. So you have the D0 is going to be D0 is the only rows. I think you. And D1 and anything from D1 is going to be the previous rows, or I should say, given the current index, the next amount of rows, or the current columns for the whole set. So the big sell, what I'm trying to sell you on is that the amount of computation required to multiply A0 and A1 is the dimensions of D0 times the dimension D1 and D2. If you do that multiplication, you'll end up with the amount of multiplications required to do that operation. It's really, it's worth doing one little toy example to sort it. So I'll even, like, it takes, 1 minute, so do that, please. Do a small just self-directed learning. Just do some matrix multiplication with just like 3 elements. It doesn't take long to do, but it's also trivial enough that I don't want to do it in lecture. It turns out that there aren't a lot. So if you think about, if you given a set of, A0, A1 to AN, given an R set, how many ways do you think, given the placement of one bracket, how many ways do you think you can split the set? It turns out if we consider a certain way of placing brackets, so if we consider placing brackets such that we're going to sort of split the set, that we can get away with considering subdividing the set such that there's one bracket, for say A0, A1, might have a bracket around it, and then we might have, actually just do these. So the goal really is to find the best placement of brackets such that a little change like this actually helps out a lot in terms of the amount of complications. Brackets. So our input will be R. And it turns out, I'll do a sort of example to sort of get things rolling with V brackets. So let's consider 1. I don't know, sometimes I do my notes and I think I want to do something and then I start doing it and I realize that it's really quite tedious. Okay, so. Yeah, I think I wrote one too many. Or no, I didn't do that. So how many combinations do we have here that yield unique totals? How many unique totals? So think about it for a second. For multiplications. So right away, we can kind of get rid of some of them. I mean, these three are the same. These three are the same. Can you guys see that? Like, I mean, this is saying do A1 with itself. It doesn't make sense, so that's fine. A1, A2, okay, that's going to happen anyway by virtue of the ordering. So these three are the same, which is also the same as this one. I feel like I forgot one. This is unique. Oops. I am just mangling the chalk today. And there should be n minus 1 ways. So 3, there should be, oh, so there's 2 ways, okay. So it should be, so that's interesting. Like in terms of the structure of the problem. I'd recommend kind of proving to yourself that number 1, that these numbers work, and that number 2, that this works. Does it kind of make sense though? Given the number of multiplications? Because you're going to be doing the same procedures here when replacing these brackets. But, you know, given the value of where the brackets are placed, where you're looking at splitting the set, you know, if we consider the idea of 2 brackets even, it's kind of going to get fun. So we're going to consider sort of unique splits with the brackets that generate unique subproblems or unique sort of computational difficulties. Okay. So, in the real problem, so in the problem with unlimited brackets, you may have something. Might have something like that. And the idea is we want to optimize this. It's pretty weird. Can you guys think of a way to get started with this problem? This is where we want to end off with the ideal bracket placement. So if we talk about how, you know, this, how like we want to start here.
overlapping, like,
Yeah, like even we might even before you guys love to consider the overlap first, but I think even before we consider overlap, we should think about what the optimal substructure might look like. So what, like, if we think about what's the optimal substructure, what's the subproblem that we might have that we could